Okay, once again, back to the session. We are continuing from the previous topic. Last session we completed about semiconductor and its important areas to be covered, and that's an easy chapter. If you go through that important concept, 7 mark easily can score. Now the next easy chapter in your syllabus is this one, atoms and nuclei. Okay, here mainly we have to start with Rutherford atom model. This is a very important, frequently asked, repeated question. So on Rutherford atom model, what are the important key points we have to follow there? First one, they may ask what is Rutherford atom model or Geiger-Marsden. So this is a usual confusion. Rutherford and Geiger-Marsden is the same 3 persons. They conducted this experiment. Sometimes this can be asked as Rutherford experiment, or it can be asked as Geiger-Marsden experiment or alpha scattering experiment. Here, first what you have to do, you have to just show the experimental setup. Okay, here this is a lead chamber, uranium source. Here we are keeping a gold foil and we are showing this is using a collimator. It is accelerated, W is equal to Q into V. So alpha particle gain and kinetic energy, this alpha particle colliding here, that scatters at different angle. Here we keep a detector. So the first point we have to say, the experimental setup are shown in figure. Lead chamber, source, collimator and screen. The scattered alpha particle can be detected with the help of detector. Okay, fine. Now next one, in theoretical part if we go, we have to say that why this experiment conducted, Rutherford, Geiger and Marsden. Okay, from that experiment they got a graph like this. N theta, number of alpha particles scattered at a particular angle. This is the angle of scattering. And the graph they observed like this. Okay, here 0, 90, this is 190. This graph interpretation of this point, this shows most of the alpha particles 0 degree, traveling almost straight line. Some alpha particle going above 90 degree, some are hardly here and there 180 degree. So these are the important points you have to mention in this derivation. First one, experimental setup, roughly you have to show. Then this graph. Then what is the importance of this graph? Most of the alpha particle traveling along straight line. Very less number above 90 degree. Some are 180 degree. Now we have to explain comparison with Thomson's model and Rutherford atom model. In Thomson's model, charges are equally distributed. Okay. Therefore, what Rutherford, but according to Rutherford, see there are some alpha particles scattering more than 90 degree. So at what then Rutherford conclude, or what he postulates that, see, when a fast moving alpha particle, it's heavier than proton or neutron when it approaches an atom. Coulombian force of repulsion makes them scattering in different way. So what happens if it is a Thomson's model which is uniformly distributed, then alpha particle would not have deflected larger angles. It will be only very smaller scattering angle, we will see. But here in gold foil experiment, they are deflecting at very larger angles. So for example, this explanation for that, for this graph. See, charge particle which is coming exact head on, deflect back. So theta 180 degree. Charge particle coming to this periphery, deflecting back like this. Okay. So this is more than 90 degree. Charge particle which are little more far, going less than 90 degree. Less than 90 degree. Other charge particles are almost going straight line. So from here, important point you have to mention here. First of all, we have to make a small comparison with Rutherford and Thomson's model. It is clearly given in the note. In Rutherford in Thomson's atom model, charge particles are equally distributed. What Rutherford says, if in this case if alpha particles are deflecting at larger angles, it cannot be like a Thomson's atom model. All protons, for example in gold there are 79 protons, all this should be accumulated into a very small region that is called nucleus. That's why the alpha particle 180 degree deflecting, which is coming at the periphery deflecting more than 190 degree and little more far deflecting less than 90 degree. Then many are going straight, that shows interatomic spaces. So main value points, comparative Thomson's model, why this deflecting larger angles, you have to explain. That led Rutherford to speak about nucleus. That point is important key point. Second thing, this graph, using this graph, why this different scattering occur based on this graph, we have to explain. Okay, these are the main thing we have to bring in the explanation of Rutherford atom model. Okay, then after that, next question can be asked from here. So this graph should be there, this explanation should be there. 1 year, around 5 years back, this question asked on the board. Then here, example questions 12.2. In Geiger-Marsden experiment, what is the distance of closest approach? There is a question, is there example 12.2, page number 419. You can see this question, you can solve it. Okay, direct question using Coulomb's inverse square only, this is shown. Then next one, electron orbit, Bohr atom model. In Bohr atom model, expression for radius, then expression for velocity, then expression for frequency, wave number. So these are very important, and there some values are given for radius of the atom, velocity of the atom, time period of the atom. All these formulas you should by heart. Okay, so that constant numbers is coming 5. So here, this one, basic question, another type, derivation can be asked from you. First of all, radius. What is the expression for radius? We have to derive from 3 Bohr postulates. You have to write, from there you have to obtain expression for radius. And the radius formula we know, n squared x squared divided by 4 pi squared n k z d squared, like that. From here, except n squared, if you solve, you can get the constant value. Rn is equal to 5.3 into 10 to the power minus 11 n squared meter. Like this constant, if you by heart, it's easy for you, because question can be asked, what is the radius of the first orbit? N is equal to 1. Second orbit, n is equal to 2. Third orbit, n is equal to 3. In that case, just substitute get n, this constant value of the by heart. Similarly, velocity in that orbit, if you want, this formula can be used. Vn is equal to 2.18 into 10 to the power 6 Z by n, meter per second. And here Z is equal to atomic number, that is 1. N we can choose which orbit. Similarly, time period n, Tn is equal to 1.52 into 10 to the power minus 16 n cubed by z squared. So these are kind of questions you can see textbook exercise. They are asking radius, find the radius of the second orbit, velocity of the second orbit, time period of the second orbit. Then their explanation is very complicated, no need to go that way. You can directly substitute this formula and we can get radius, velocity and time period of the electron in particular orbits. Okay, next one we have to speak about energy. Okay, when we speak about energy of electrons in particular orbit, we know E is equal to minus 13.6 electron volt. Okay, divided by n square. This is a formula for energy of the electron in particular orbit. Based on this question, total energy, kinetic energy, we can get the formula half mv square. Using Bohr postulate, when we derive, we will get mv square is equal to k is d squared by r. And potential energy is equal to minus k is d squared by r. Total energy is equal to C minus 1 plus half, that will be minus half k is d squared by r. Here you can see kinetic energy and total energy magnitudes are same. See, Ek is equal to Et. And similarly, Ep if you are taking, see Ek multiplied by 2, you will get this value. So Ep is equal to 2 times Ek or 2 times Et. And one question is there in textbook also, previous year also they asked, minus 13.6 is the total energy of the electron in the first orbit. Then what will be its kinetic energy? That means same thing plus 13.6 electron volt. Potential is twice, minus 27.2. This kind of question also very important. Previous year they asked. So this relation between total energy, kinetic potential also you should keep in your mind. Then Balmer series, Lyman spectrum, Balmer series, Lyman series. From that they can ask. In that we know when we speak about atomic spectrum. These are the topic questions we are asking. This is first orbit, second orbit, third orbit, fourth orbit, fifth orbit, like that. N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4, N is equal to 5, N is equal to 6, N is equal to 7, like that, N is equal to infinity. Second orbit to first orbit, third orbit to first orbit, fourth orbit to first orbit. This is known as Lyman series. We know that Lyman series. Next one, third to second, fourth to second, 5 to second, 6 to second. This is called Balmer series. Your first line is known as H alpha line, H beta, H gamma, H delta. These are the lines. Okay. So this is called Balmer. Next one, Passion, then bracket. They are all. This is ultraviolet. This is visible light. These are all infrared region. From your expected question, what is the shortest wavelength? See, wavelength E is equal to h nu. Frequency is low, energy is low. Frequency C is equal to nu lambda. Okay? So nu frequency increasing, wavelength usually decreasing. So remember, energy decreasing, frequency decreasing, wavelength increasing. Suppose they are asking what is the shortest wavelength in Lyman series. Shortest wavelength means highest frequency. Isn't it? Highest frequency. So infinity to this level you have to take. In case they are asking highest wavelength. Highest wavelength means shortest frequency or smallest energy. Then you have to take this level. Year to year transition gives highest wavelength or smallest frequency or smallest energy. Like that I can ask what's the wavelength of H alpha line, H beta line, H gamma line. Like that question can be asked. Okay, then using Rydberg constant, you know, final formula, using Rydberg constant, the wave number 1 by lambda is equal to R into 1 by N1 squared minus N2 squared. So using this, determine the wavelength of, say for example, 4 to 3 or Passion series, what the first line, or Lyman series, what second line, like that, they can ask. So that's all important area to learn. Okay, so basically, here the derivation of radius, velocity, time period usually they ask from this topic. This is atoms. Then when we speak about here nuclei, okay. So this is the first thing you have to focus. Question number example 12.3. It is found experiment that 13.6 electron energy is required to separate a hydrogen atom into proton and electron. That example you have to see. Then atomic spectra I told you in textbook, page number 421, that you have to go through. Then Lyman series, that bracket series or that series equations you have to study. So this is the main question asked from that chapter. Okay. Then example 12.4 you have to go through. Then here it comes. Okay, this is a question from that chapter usually come. Okay, then there are some deleted topic in the first textbook that you have to delete. You have to focus on second textbook. Okay, a new textbook available now. Then next one is coming nuclei. In nuclei, which are the areas mainly we have to focus? In nuclei chapter, first one, mass defect. Okay, mass defect. So based on mass defect, question can be asked. What is the formula for mass defect? For example, first one, let us see, we will go in the order size of the nucleus. From the size of the nucleus, question R is equal to R0 8 to the power 1 by 3. Question based on this will be asked. This is actually radius of a nucleus. Radius of the nucleus. R0 is empirical constant 1.1 into 10 to the power minus 15 meter. So, and this is mass number. So usually they give two atoms. So for example, uranium 92, 235 and uranium 90 to 238. What is the radius of the ratio of the radius? So we can write R1 is equal to R0 into A1 to the power 1 by 3. R2 is equal to R0 into A to the power 1 by 3. If you divide R1 by R2 is A1 by A to the power 1 by 3. Here mass numbers we have to use. So 235 divided by 238 to the power 1 by 3. Like that, based on this question, atomic radii question can be asked. Okay. Ratio of the two mass number will give. They will ask you to find out ratio of the atomic nuclear radii. For example, mass number of two element is A1, A2, 0, 1 is to 8. What's the mass number of radii of their nuclei? Then we have to write root of here. A1 by A2 to the power 1 by 3, that is 1 by 8 to the power 1 by 3, that is 1 by 2. Like this question can be asked based on this formula, first important question formula. And here, question number 13.1, the textbook, very complicated explanation is given. You can use directly nuclear density formula that I will show you. Nuclear density, we know, rho is equal to mass by volume. So this is Na, mass of one nucleon into mass number divided by 4 by 3 pi r cube. So 3 Na divided by 4 pi r cube. So 3 Na divided by 4 pi r, already we have the formula. R naught into a to the power 1 by 3 whole cube. This is cancelled out. Then density is equal to 3 Na divided by 4 pi into r naught cube. A cancel. It is independent of mass number. Okay, then we get a constant value 2.92 into 10 to the power 17 kilogram per meter. It approximately this value. Please confirm with the notebook. This approximate value. So this is a constant. So directly we can write this value 2.29 into 10 to the power 17 kilogram per meter cube. Because nuclear density is constant for all elements. Another question can be asked, the ratio of the mass numbers of two elements is 1:8. What is their nuclear densities? So 1:1. Okay, this is the answer. So this kind of question repeatedly they asked. So example 13.1, unnecessarily they made it very complicated textbook. You can directly use this formula 3 Ma by 4 the power, directly can write the answer because nuclear density of every element remain constant. Okay, then 13.2, calculate energy equal to 1 gram of substance. That also we have done in notebook. You can just go through, it's a derivation. Then mass defect. When mass defect question comes, this is a formula for mass defect. Delta M is equal to Z, atomic number into mass of proton, plus A minus Z, neutron number into mass of neutron, plus from here this total minus XAZ, an element, and mass of that nucleus formed. This will give you mass defective unit. Then binding energy if you want, we have to calculate this delta M into 931.5 mega electron volt. Based on this question can be asked. For example, ferrum 2656. If you want to find out binding energy, you must write delta M is equal to 26 proton, 26 into mass of proton. This constant will be given in the question paper. That will substitute here, plus A minus Z, 56 minus 26. That is 56 minus 26, 30. Isn't it? 56 minus 26 is 30. 30 into mass of neutron. This one, M. Fine. Then minus mass of the nucleus ferrum also will be given. That also substitute. The difference will give you delta M multiplied by 931.5. You will get binding energy. In case it has binding energy per nucleon, that should be divided by A. So these kind of numericals we saw in notebook or textbook also. These problems are given. You can answer this kind of question usually asked from this chapter. Then most important one, page number 444. This very frequently asked question, graph between binding energy per nucleon and mass number. Okay, in this graph I will plot it. This is the way you have to plot. Okay, page number 444, old textbook. You can see that. Okay, look here. This is the way graph to be plotted. Here 50. Then 100, 150, 200, okay, 50, 100, 150, 200, 250, you have to mark here. Here 2, 4, 8, 6, 10. 2, 4, 8, 6, 10. Mega electron volt per nucleon you have to mark here. And here mainly we have to mark here hydrogen. Hydrogen comes in H1 here. H1, then H2, then it goes to helium. Helium comes just above 6, between 6 and 8 helium. 6 and 8, somewhere near helium. So this hydrogen, helium, lithium. Lithium comes just less than 6. Then you can go to carbon near to 8. Carbon near to 8. Carbon 12 near to 8. Then straight away you can go to ferrum. Okay, ferrum comes about 56. Then you can go to uranium. Why at least this many points should be there? Because in the explanation they will ask what is the importance of the graph. Okay, if you can add more elements, if you remember, you do it, but minimum this many, because this graph we are explaining this way. Okay, less than 30, mass number 30, hydrogen H1, H12, etc. having very low binding energy per nucleon, they have the tendency to combine and come into middle mass region, which explain the probability of fusion. So this should be marked here. Then we say about these peaks, okay, helium, carbon, etc. There are some peak points. It shows they are relatively high binding energy with the neighborhood. So that also we should mark there. Then we are going to highest element for ferrum 2656, 8.75. This is the highest binding energy, most stablest. Then again uranium 92 to 35, less than 8. It is again unstable. And elements having more than 170 mass number has a tendency to split and come into middle mass region with the release of energy. So these are the important points you have to mention about this graph. So first you have to draw this graph, at least with these elements I marked here, or maximum how many you can bring. But this cannot be accepted. And explain less than 30 low mass region, 30 to 170 middle mass region, 70 more than 170 to above, that is heavy mass region or high mass nuclei. So what is the importance of the graph? We can say in low binding energy per nucleon shows they have a tendency to combine and come into middle mass region with the release of energy. That's called nuclear fusion. Here energy release is because of mass defect. Similarly, more than 170 heavier nuclei like uranium and low binding energy per nucleon, they have the tendency to split and come into middle mass region with the release of energy. There also reason for release of energy is mass defect. So these 3-4 points should include in this explanation. So this is very important question you have to study. Okay, in the notes, go through the notes and make a thorough learning out of it. I'm just giving for only brief idea. The nuclear force. What are the properties of nuclear force? Like it's a strongest force, short range force. It happens between every nucleons like proton, neutron. Irrespective of their charge, they do not obey Coulomb's law. They start becoming operative at 4 Fermi to 0.4 Fermi. At 4 Fermi to 0.4 Fermi, they are attractive. Less than 0.4 Fermi, they are repulsive. And the graph also very important. Usually in the graph, okay, like this. This is 4 Fermi. This is 0.5 Fermi. Here attraction. This negative side shows its attraction. Positive side is plus. Potential energy also same graph. This is page number 445. If you check, you can see these graphs. Okay, that's important graph. Then radioactivity and not in syllabus. Okay, then we have to go to nuclear fission. What is nuclear fission? Nuclear fission is your nuclear fission is the phenomenon of splitting a heavy nuclei into middle mass nuclei with the bombarding of a slow neutron into it with the release of large amount of energy, and reason for that is mass defect, and it released because of mass defect. Okay, similarly, then there are some examples in the textbook. 3 examples are there. At least you have to study uranium plus neutron splitting into barium and krypton and 3 neutron. At least one example you should buy out. Textbook, there are 3 examples given. Similarly, nuclear fusion is also very important area. It is a combination of heavy nuclei, lighter nuclei. It is a combination of lighter nuclei and come into middle mass nuclei with the release of energy and large amount of mass defect they are taking place, that only this energy release. It is the combination of two lighter nuclei and coming to middle mass nuclei with the release of large amount of energy. Reason for energy release is mass defect, and this is usually observed in sun and stars. For this, high temperature and high pressure is required. While in nuclear fission, a slow neutron has to use to bombard the nucleus to split into smaller fragments. So this difference also you must know. Nuclear fusion, lighter nuclei at high temperature, they combine and releasing energy. Nuclear fission, heavy nuclei like uranium, bombarding with slow neutron and splitting into middle mass nuclei. Uranium, barium like that. Okay, fission fragments are not predictable, it varies. Examples given in textbook, you can see that. Okay, so these are the main areas in this chapter. Nuclear fusion also, some examples given in textbook and notebook also I gave, just by heart that formulas, 3-4 examples they may ask. So this is a chapter, atomic nuclei. Here if you focus, you can score the mark and take new book, because old book has so many unnecessary portions which are already deleted. So take new book or tell your friend to share that exercise questions and try to solve it. That we can easily solve. Just look at the notebook with the given formulas, you can solve it easily. Okay, then next chapter we have to go with dual nature. In dual nature, more important thing, okay, than graph. So first of all, definition. What is work function? Now we are discussing about the chapter dual nature of matter. Okay, there first point we have to speak about. You should be familiar. What is work function? What is threshold frequency? Work function is the minimum energy required by a metal to release one electron or to overcome the potential barrier of the metal. Threshold frequency is the minimum frequency required by an incident photon so that its energy h nu naught is equal to work function. Only for the frequencies above this threshold frequency, emission takes place. So these are the important points. Question can be asked: what is photoelectric effect? What is threshold frequency defined? What is work function? And Hall wash experiment. In that, 3 graphs are there, right? This is intensity photoelectric current. Photoelectric current. This is intensity of incident photon. So graph will go like this. Then another graph like this. See here, this again photoelectric current. Zero potential. This is accelerating potential. Accelerating potential. This is decelerating or retarding potential. Retarding potential. So your graph goes like this. This is intensity I1, I2. Here I1 is greater than I2. In the question if they say I2 greater than I1 means here you have to mark I2, here you have to mark I1. This is stopping potential, we all know. This is very important graph. Similarly, if different frequencies you are asked to mark, different frequencies, same intensity means graph goes like this. See, same intensity I. But this is V01, V02, frequency nu1, nu2. Okay, when you come to frequency increases, stopping potential also increases. Then these 3 graphs are very, very important graph. Question can be asked. Okay. Next graph, this one. Okay, this is a kinetic energy frequency graph. So graph goes like this. This is threshold frequency. Kinetic frequency. This is nu. So here slope of the graph gives Planck's constant. Instead of this stopping potential, if you are taking stopping potential V0, then slope of the graph gives h by u. Kinetically frequency graph gives only h. Stopping potential frequency graph gives h by u. So this is slope. Based on this, question can be asked. Okay. Then another question. The values will be given. They will ask you to calculate work function. Then you can calculate h nu naught, h nu naught a, h nu naught. Here. Suppose there are 2 metals like this. This is A, this is B. For all, slope remains constant because h by is constant. This is the work function of first metal. This is the work function of second metal B. So they will ask you to calculate which metal has more work function. Another question, if a photon is falling at the same frequency, which will emit more kinetic energy. So formula you should know, half mv maximum square is equal to h nu minus work function. This formula you must know. So based on this is called Einstein's photoelectric equation. Question can be asked. So mainly from here, this graphical questions will be asked. Okay, what is the slope of stopping potential graph? What is the y-intercept? Minus w naught a by e. This question can be asked. This is all I gave in the notebook. You have to focus the given questions. Okay. Then next topics there. Next one, energy. Energy stored by energy in a next one, de Broglie hypothesis. We know every moving particle is associated with the wave nature. So this is known as de Broglie wave. So based on that, they may ask what is de Broglie wavelength? H by mv. Based on this, numerical can be asked. De Broglie wave. Okay. So here there is a formula relation between energy, de Broglie wave and energy is h is the root of 2mE. Based on this, 2 alpha particle, 1 alpha particle and proton, what will be the ratio of their de Broglie waves? Like that question can be asked. Then another thing, h divided by root of 2mQV. This based on this, numericals can be asked. Examples I gave in the notebook, please check. Okay? So this is about a dual nature of this one. Then if we speak about wave optics. In wave optics, there are not derivations as such. Mainly two derivations they can ask. Obtain, okay, using Huygens wave theory. Using Huygens wave theory, obtain, that means loss of reflection I is equal to R. So we have to mark here infrared wavefront. This is CT. Using a compass, measure here. Using a compass, take this length and from here cut an arc. So here you will get an arc. Okay. This is the tangent. From center to the tangent, if you mark, that's a ray. This is a wavefront. And here this is I. This is R. You have to prove I is equal to R. There's a derivation like that. It's very important to mark derivation. Similarly, using Huygens principle, refraction also very important. Refraction is more frequently asked than reflection. See, this is the incident wavefront. Okay, this is C1T. And here they are refracting like this. Okay, this is C2T, this is I, this is R. From here we can prove C1 by C2 is equal to sin I by sin R. Like that, we can obtain expression. So this is also important using Huygens principle, proves Snell's law. And they may ask rarer medium to denser medium as well as denser medium to rarer medium also. Question can be asked. Okay. So that is the main thing you have to understand in wave optics. Right? Important two derivations. Then from interference, I can ask what is the definition of interference. It is a real distribution of energy when the waves are reaching at a point. And definition of diffraction. It is bending of light over the obstacle or spreading of the light when it is obstructed. This is the diffraction. And under what condition this interference diffraction can obtain. So condition for sustained interference is very important. Sustained interference S by S less than lambda by D. Okay, so here S is the size of the original source, capital S is distance between original source and screen, wavelength and distance between coherent sources. Based on this also, question can be asked, what's the condition for sustained interference, what is coherent sources, and when original source is keeping away, how does it affect fringe pattern, distance between two slits are reducing, how does it fringe pattern. These kind of questions I have given in the notebook, that's very important, they can ask a question. And diffraction also same way, when width is reduced, how does intensity of central bright region change, how does width change, and what is the relation between interference and diffraction. There we study the overlapping region of two diffraction pattern, interference pattern is produced. All these kind of questions also is very commonly asked from wave optics. Okay. Then we are going to ray optics. In ray optics, first derivation, mirror formula, and second one, lens formula. Mostly they will go with virtual images. Either object is placed between optical center and focus, or convex mirror. This is the main thing they are asking in mirror and lenses. But not that area, not very frequently asked. In that derivation we considered, sometimes if they want to make the paper little lighter, they can ask, but it's mostly 10th standard based derivations that. But they may ask it in syllabus. Mostly your level, it comes with the refraction side. Okay, and numerical can be asked, magnification, focal length, that kind of things they can ask. But when we come to lens, it's more frequently asked question coming from lens. First one, refraction through this curved surface. That formula, that means minus u of n1 plus v of n2 is equal to n2 minus n1 by r1. R, like this formula, two surfaces formula. And when they are combining, we get the lens makers formula. That's also very important. Very, very frequently asked question. And numerical based on this lens makers formula is very important. Even conceptual question I gave in notebook. Study thoroughly. You will take questions from this area. Okay, when a lens is cutting into half, what will be the new focal length? What will be the refractive index when a lens immersing into water? When a red light and violet light is using, how does a focal length is being affected? This kind of question very frequently asked from ray optics. Another one, most important, most of the year if you are taking, if you are very unfortunate only, this question will not ask. Otherwise, every year this question asked. Okay, here there's a prism, refraction through the prism under minimum deviation condition. So you have to draw the diagram and get the formula sine n is equal to sine a plus delta n by 2 by sine a by 2. Draw a graph also, RILD, this graph. This is very important 5-mark category. Okay, then another question important, microscope, near adjustment, and telescope, normal adjustment. Second priority, microscope, far adjustment, telescope, near adjustment. But most commonly asked, microscope, compound microscope, near adjustment, and telescope, far adjustment, normal adjustment are very frequently asked. It does not mean others cannot ask, it may ask, but this is more frequently asked question, more probability we are telling you. So priority learning I told you, the previous day of exam and all, instead of learning whole thing, this more important frequently asked question you should make thorough in the previous day of the exams. Okay, right. Then, so another important area and most important, many years this question repeated about total internal reflection. First thing, before total reflection, we must know what is the meaning of critical angle. What is the critical angle? When the light ray is traveling from denser to rarer medium, okay, usually light ray went away from the normal. This is called angle of incidence, is angle of refraction. As angle of incidence increasing, angle of refraction also will increase by Snell's law. Here we can see in the case of water to vacuum or water to air, approximately if you are taking this angle, when it is around 40 point something, 2 degrees, something like that, you can see this light ray exactly traveling along here. That means angle of refraction will be 90 degrees. So here, then this angle, at a particular angle of incidence in the denser medium, this angle of refraction is 90 degrees. So this angle is known as critical angle. If you are taking glass air media, this is around 41 point something, 41 degrees something it will come. So that point it will be 90 degrees. So we can say here critical angle is an angle of incidence in the denser medium for which angle of refraction is 90 degrees. And for the angles below, this will lead to refraction, and above this will lead to reflection. Here 100% reflection you can observe, that's the total internal reflection. So based on this we know Snell's law, denser to rarer, sin I by sin R. Okay, so denser to rarer, because this will observe only from denser to rarer when light are traveling. When angle of incidence is equal to the angle called critical angle, that's a characteristic angle for every pair of media. So I told you for glass air it is 41 point something, approximately 42, and for water here 48. For diamond air media it is around 24 degree, and this is changing for different colors also. So when angle of incidence is equal to critical angle, we can say denser to rarer is sin IC divided by, then this time R will be 90 degree. This is a condition. Then here n denser to rarer is equal to sin IC, and rarer to denser is equal to 1 by sin IC. So denser to rarer if you are taking, you should take sin IC, rarer to denser you have to take 1 by sin IC. The purpose of this, rarer to denser will give you absolute refractive index. So relation between absolute refractive index and critical angle is n is equal to 1 by sin IC. So this is one important relation. And above critical angle, I told you light ray will completely reflect into the media. This is called total internal reflection. So question can be asked, what are the conditions for total internal reflection? When the light ray is traveling from denser to rarer medium, light ray should travel from denser to rarer medium. This is the first condition. And angle of incidence should be greater than critical angle. In this condition, total internal reflection we can observe. And applications of total internal reflection also very important. Example, optical fiber. If I take optical fiber, this consists of a core. Here there is a core and around 1.68, this is 1.44. This is called cladding. So light ray should go from denser to rarer medium. In this case, when the light ray enters here, okay, if this angle of incidence is greater than critical angle, complete light ray reflecting back into the same medium. This is called optical fiber. This is mainly used in optical communication, endoscopy, etc. Then there are many atmospheric observations we can see, like mirage. In the desert, we see image like, in desert, for example, during hot summer, air will be hot here. So this air, hot air acting like a rarer medium, upper layer will be cold up. Therefore, light ray is traveling here subject to total internal reflection. So if anyone look from here, they feel this appear to be coming from here. This is called mirage. Okay, so this is another example. Then another example, looming. Like in so many examples we can see, this can be asked. What is the reason for this mirage? What is the reason for looming? So we can say this total internal reflection. Another thing, TIR prisms. In TIR prisms means, look here, for example, this will be 90 degree angle, these two 45 degree angle. If the light ray falls here, this will go to 180 degree deviation. For example, here angle of incidence is 0, angle between incident ray and the normal is 0. So here light ray refracts in the same direction, and here angle will be 45 degree. For glass air media, maximum it can be 42. So if the angle of incidence greater than critical angle, that means 45, 100% reflection taking place. Here also same thing, 100% reflection taking place. So this is 180 degree light can be deviated. Another example, light ray 90 degree deviation. See here angle of incidence is 45 degree greater than critical angle, it's reflecting back. And another question can be asked this way. See, this is also a TIR prism. Light ray which are reaching here, falling here, coming out, and here this way. Here it is 180 degree inversion. So these are mainly using in binoculars and telescopes, periscope, these kind of applications such as it is given in notebook, just our thorough learning out of it. And based on this, main numerical can be asked. For example, here two colors will be given. For example, red or blue, three colors, say for example green. So what will happen? Which of the colors will come out? Here you have to check the critical angle of the red, blue and green. Okay, and if the angle of incidence here greater than critical angle, light ray will reflect back. If angle of incidence less than critical angle, it will refract. So according to the given value, you have to calculate critical angle for each colors, and you should say which are refracting and which are reflecting. So these are the important points from critical angle and total internal reflection. So from this area also, read the notebook and thoroughly how to learn all the exercises I have given in the notebook. Okay. Then this is about ray optics and wave optics. Then we have to go to electromagnetic wave. In electromagnetic wave, the spectrum, electromagnetic spectrum is very important. Okay, gamma ray, X-ray, ultraviolet, visible light, infrared. Then what is next? Microwave, radio waves. All this specimen you should know in order. Their frequency range, wavelength range, and their uses, their production, mainly their application. Definite question. And there's one question I gave you, an equation for electromagnetic wave is given. And from that, they will ask determine amplitude, wavelength, frequency, like that. And the graph of electromagnetic wave. See, this is an electric wave, this is a magnetic wave, and E is equal to E naught sine kx kx plus omega t volt per meter. This is EY, this is X. Then B, write B. First they give expression for electric wave, then they will ask you to obtain expression for magnetic wave. That means B is Z here. See, Y and X is gone, then B is Z is equal to B naught sine kx plus omega t Tesla. Like this, you should be able to write this graph as well as related relation, which indicating vibration of electric field and magnetic field and direction of the wave. Based on this, question can be asked, like in the notebook. That's 3-mark question can be asked. Okay, so this is our main content about electromagnetic wave. Okay, so in the last two sessions, we have seen the chapters of the second book. Okay, the important chapters. Hope it may be useful for you. Now let's go with the topics of first book. Okay, so here we are starting from the beginning. Electrostatics, which are the important questions usually coming in the frequently asked questions. Okay, first one, let us see about electric fields and electric charges. The question can be asked, electric field due to charge, positive charges, positive point charge, negative point charge, like that, and the difference between electric field between two charges separated by a distance. These kind of 1-mark questions can be asked. This is the first thing. Second thing about this one, charge. When a charge is placing above a metal plate, how we can draw electric field here? This positive charge develops negative charge due to electrostatic induction. Okay, so therefore, based on this electrostatic induction, question can be asked: a plate or between two plates, like positive here, negative here, how the electric field lines can be drawn. So this will be negative, here it is positive, here it is negative, here it is positive. So here electric field can be drawn this way, and these plates are coming closer. So these type of questions, or a thin shell and a positive charge is placed here, how does electric field come? These are the type of questions usually from this electrostatic induction. Now many times this 1-mark question category, this question asked. That means a charge is placed near a metal, maybe plate or a shell. How electrostatic induction producing field onto the other side on metal plate and draw electric line of force. Okay, these are the main questions from electrostatic induction they are asking. Then if we come to this one, quantization of charge, they can ask Q is equal to plus or minus NE, but not very common question, that one. Then Coulomb's law. By Coulomb's inverse square law, main question, superposition principle, they can ask. Okay, in vector form. For example, we know Coulomb's law question, F is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R square. Based on this, many questions can be asked. For example, charge is in equilibrium. Here a charge Q is placed. Here another charge 2Q is placed. Okay, what can be the third charge so that charge comes to equilibrium? These kind of questions can be asked. Here we know, in such cases, we can equate repulsion, attraction, and to attraction should be equated like that. That means in order to find out magnitude of the third charge, we have to equate these two, repulsion and attraction. If you want to find out the distance of the third charge to be placed, this attraction will be equated. This way we have discussed this in notebook, that part you have to focus. Okay, equilibrium conditions. Another thing, for example, the charge particle placed here and resultant forces based on that. This is first thing, numerical based question can be asked from this area. The next one, position vectors, using position vectors, intensity, electric field intensity questions can be asked, same manner. So here, so for example, charges Q1, Q2, Q3, Qn, like that. Different charges are distributed at R1, R2, R3, Rn. What is the intensity at the point P? Obtain expression for it. So we mark here R1P, then here R2P, This is intensity at the point P by charge particle 1. Intensity at the point, this is by 1, this is by 2, then by 3, charge by 3, like that you have to mark it and obtain expression for 3 more category. This question asked. Resultant intensity is equal to E intensity at the point P by 1, intensity at the point P by 2, intensity at the point N. Then we are writing here 1 by 4 pi epsilon 0 Q1 divided by P1 by Rp minus R1 whole cubed into Rp minus R1, like this, and plus, like that repeatedly we are writing. So this question based on superposition principle they asked. This also in the notebook, please refer this derivation. Okay, that's a derivation based on this. Then here plus 1 by 4 pi epsilon 0 q to Rp minus R2 and Rp minus R2, like that kind of vector addition. Okay, then next similar way, intensity due to triangle, 1 charges, 3 charges placed in here, what is the intensity at the center, like that kind of questions can be asked. And next important area here, Gauss theorem. Okay, sorry, electric flux. In electric flux, using the formula phi is equal to E dot ds. Based on this, problems can be asked 2-3 times. This question asked like this. Say for example, this is a charge particle x, y, z. Here a cube is placed, and here area. This is left, this is right face, and here what is the net charge placed inside the cube, or what is the net charge placed inside? Like that one example problem here we have. Okay, so about superposition principle, that's given in page number 15 textbook, old textbook. Then example in page number 16 is important. Then next one, see here intensity in page number 20. There's a diagram given, page number 20, figure 1-2. That's the question I told you they asked in the previous year question. Then here, this question, example 1-9, is a possible question. Then next one, page number here. Just a minute. That's what Gauss theorem question was there. Page number 35, example 1.11, the old textbook. That numerical they asked before. Or just next page, there is one question in the cylinder. Page number 36, that numerical also, very important, cylinder and 2 charges placed here. So here we have to find EDS cos theta, EDS cos theta resultant intensity. From that we can find out flux and net charge. So refer textbook, that question is very important question. Then after that, if you go to Gauss theorem, most important one, thin sheet. Intensity due to thin sheet. Okay, so that is E is equal to sigma by 2 epsilon naught. This intensity due to thin uniformly charged sheet is very important derivation, very frequently asked question. And from that, 1 more question, 2 more questions can be asked. Suppose this is a sheet, this is another sheet. Here this is positively charged, this is negatively charged. This is sigma and sigma b. Sigma is greater than sigma b. What is the intensity in the region marked 1, 2, 3? So obtain expression for intensity here, intensity here, intensity here. This is very frequently asked question. Refer notebook and study this very important area of frequently asked questions. Then similarly, thin wire. Okay, this was also very important. Thin wire, positively charged thin wire. So intensity at a distance E is equal to 1 by 2 pi epsilon 0 lambda by r. Based on this also derivation can be asked. And once they ask a question in an electron moving around here, what is the force acting onto it? So based on this question can be asked, based on the intensity of uniformly charged thin sheet. These two are high priority in this Gauss theorem application. Then sphere is the second priority. Sphere also an important one, but most probably they ask thin sheet and thin wire. That's a question, most frequently asked question. Then if you go to electric dipole, the torque acting on dipole, or question can be asked, for example, here this is a graph and they are saying a charge, positive charge 5 microcoulomb is placed 0.05 centimeter. Another one minus 5 microcoulomb, 0.05 centimeter. And this is calculate the net charge and net dipole moment. These kind of numericals in 2-mark category many times are repeated. Second part, torque derivation part. Okay, torque acting on an electric dipole placed in a uniform electric field. Very frequently asked 3-mark question, or along with this 3-mark question and numerical also can be asked. Then it comes to the category of 5-mark question. Torque acting on an electric dipole placed in a uniform electric field. Another 1-mark category question from here. Once they give, for example, an electric field like this. There is a varying electric field. We know at this point electric field is stronger because electric flux is closer. Here electric field is weaker. If you placing a dipole moment, what the net force acting on the dipole and which direction this dipole can move. And the reverse also they can ask this question like this. See, this is now electric field. The same way if a dipole is placed here, which direction this dipole can move. So these kind of questions usually asked in 1-mark category. Okay, right. Next one. Work done in turning the dipole. When a dipole is turning in a magnetic field, at 90 degree it has 0 potential energy, 0 degree it has a minus P, negative potential energy, that is minimum, 180 degree it has maximum potential energy. So expected 1-mark question, if a dipole is placed at an angle 60 degree, what is the electrical potential energy? So their formula you have to remember, work done is equal to P cos theta 1 minus cos theta 2, then energy is minus P is cos theta. So based on these two formulas, conceptual question can be asked. What is the work done in turning the dipole from stable equilibrium to unstable equilibrium, or what is the energy possessed by the dipole at an angle 60 degree? So when they ask a question based on work done, you have to use this formula, and theta 1, theta 2 you have to substitute as such. Then if they are asking what is the energy possessed by the dipole, then you have to use this formula. Remember, when the dipole moment is in the direction of electric field, it is stable equilibrium. Opposite to the direction of electric field, it is unstable equilibrium. Based on this concept also, 1-mark category questions can be asked. Okay. Then after this electric dipole, then we have to discuss about the next topic, electric potential. Okay. In electric potential, question can be asked. Then here in exercise question, this also an important question. Using Gauss theorem, see a square is given at a height a charge is placed. What is the electric flux passing through it? Answer is 1/6 times 1/0 times q. These kind of questions, electric flux, these kind of questions also 1-mark category usually they ask. Then next area, electric potential. So in textbook there is an exercise. From there many times they ask this question, electric potential, page number, this is textbook, old textbook, the not revised textbook. Okay, now next we have to start with the chapter electric potential. There we must know the definition of electric potential. It is the work done in bringing a unit positive charge from infinity to that point where potential is to be measured in that electric field. This is the definition you must know. Then based on that formula we are getting 1/4πε0 q by r, potential due to a point charge. That derivation, but not that priority, that's in the second category, priority. Then most important thing, potential due to electric dipole. See, when a positive charge and negative charge given at an arbitrary point, if you place +1 to calculate potential at the arbitrary point, then similarly potential due to an electric dipole along axial line, potential due to an electric dipole along its equatorial line. These three derivations are very important derivation. Another 1-mark category question, equipotential surfaces. Okay, equipotential surface due to point charge, and relation between equipotential surface and the point charge is 90 degree. Okay, so this based on equipotential surfaces, one more question can be asked. One example, see here, this is a graph. Draw equipotential surfaces due to a point charge or an electric field which is increasing in positive x-axis. Like this question we marked in the notebook. Draw equipotential surfaces which is increasing in positive x-axis. So it will be like this. See, here equipotential surface is far, here it is closer. So these kind of questions they can ask based on equipotential surfaces. Okay, and we should remember equipotential surfaces can never intersect, because if they intersect, electric field also will intersect, because electric field and equipotential surfaces are perpendicular to each other. Because electric field is a vector, it cannot have two directions. So that concept also very important concept. Okay, then the graph. This graph they asked before. This is intensity graph. This is potential graph. This also in textbook, page number 95. There is a graph that you should study. It's an important graph. All graphs you should go to. Okay. After this, we have to go to superposition principle of potentials. For example, they may give you a square, here a charge Q1, Q2, Q3, Q4 place. What the potential at the center and what's the work done in making a charge from here. So here potential is V1 is equal to 1 by 4 pi epsilon 0 Q1 by R, like that into 4. Potential we can calculate, and work done if you want this potential into Q0, the charge we are bringing here, you have to multiply it. So this kind of superposition principle, different shapes, triangle, square, rectangle or a circle, many problems you have done in notebook. Based on that, numeric can be asked. Most of the time they ask a question from this area of potential. Superposition principle of potential is very important. Then page number 59. That's a question. That means if this is a positive charge, they mark electric field like that. And here they are marking points A and B while moving a charge from A to B. Okay, how does the potential change? This kind of an example, 2.3 is given in the page number 59. That exercise question, many times question asked from that area. Please go through that question. Okay. Then I told you potential surfaces, potential gradient question can be asked, and potential energy due to three charge system. What is the total work done? Here Q1, Q2, Q3, R12, R23, R like that. So here potential due to this system, two charge system, three charge system, four charge system we have done. That derivation once they asked in the examination. It's very important derivation, that part. Okay. Similarly, two charges placed in uniform electric field. When you are placing in uniform electric field, we know W1 plus W2 is equal to W12. This is a total work done. W1 is Q1 into VR1 plus Q2 into VR2 plus 1 by 4 pi epsilon 0 Q1 Q2 by R12. Two charges brought closer and placed in the external electric field. So this derivation also important derivation. Okay. So these are the main thing that we have to focus in electric potential. Okay. Then we have to go to the next topic, capacitors. In capacitors, main derivations are, okay, this one. Obtain expression for the capacity of the capacitor, which affects the geometrical factors like area and distance. So first derivation, epsilon 0 A by B, capacitor placed with air. Second case, capacitor with the dielectric slab, thickness T, D is the distance. So formula, epsilon 0 A divided by D minus T by D minus T plus T by K. C is equal to epsilon 0 A by K epsilon 0 A by D. So based on this derivation can be asked, based on this derivation can be asked, based on this derivation can be asked. So any of this derivation is a compulsory question in from capacitor. Definitely you get one question from this area. Okay. Then numerical part from here, mainly they ask if area increasing, how does capacity change, dielectric slab is placing, how does capacity is affected, these kind of question. That too, when cell remain connected, when these changes are making, how the capacity is energy changing. After disconnecting the cell, when this dielectric slab is placed, how does the capacity is changing. These kind of question very frequently asked question from the capacitor. Then another question they asked, energy. When two capacitors are connected in parallel, then energy loss. From here, how much energy is lost. So here, one capacitor has, for example, 6 into 10 to the power minus 6 microfarad. This is an uncharged capacitor. Okay, if these two connect, then energy loss will be exactly half. Based on this concept, question asked, or that numerical, refer textbook, that derivation also important. Text notebook also is mentioned, that one. Right? Then next one, combinations, capacitor different combinations they may ask. Based on this, for example, here, this is K1, this is K2, this is K3, what's the effective capacity? Based on this, numerical can be asked. Okay? Or this kind of question, two capacitors connected, one dielectric slab placed here, K simplified, what will be the ratio of the energies here? Similar question in the notebook we have solved, please go through it. Okay? Then we will go to the next topic, current electricity. Important derivations of current electricity we can mark. First one, drift velocity. Very important question. Every year we get a question from here. The derivation of drift velocity, Vd is equal to A into tau. Vd is equal to minus E by m into tau. And from here we develop the formula minus NAVD in relation between current and drift velocity. Then we come to the formula rho is equal to n by n e square tau. Here our current density vector I by A is equal to minus NVD. Based on this, derivation can be asked and conceptual question can be asked. For example, if A length is double, this can be written as minus E by M into V by N into tau. If voltage is double, what happened to drift velocity? Length is double, what happened to drift velocity? These kind of conceptual question can be asked from this drift velocity. But derivation is very important. If you study, definitely you get one derivation from this area. Okay? Then conceptual questions also coming from that side. Then most important thing, this question. Another important one. See here, this is terminal voltage and current, EMF from this one. So this is EMF, this gives EMF, and R is equal to E minus V by I. Based on this, every year we get a question. Okay? Calculate internal resistance and EMF from this terminal voltage current graph. Very important area, we will have to focus on that. Okay? Then next one. Cells in charging of cells. When two cells here charging, okay, here charging, and there is a internal resistance. This is 100 volt, this is 12 volt. What is the effective EMF and what is the energy loss? How much chemical it is converting into electric energy? Like that, there are questions based on this charging of the cell. When cells are connecting for charging, positive connected to positive. So this kind of question also they ask from charging of cells. Numerical can be expected from that side. Okay. Then another important question, different graphs. For elemental metal, resistivity and temperature goes like this, and for standard resistors like nickel, manganese, etc., graph will be like this. For a semiconductor, this graph, resistivity graph comes like this. So based on this graph, questions are asked repeatedly. Okay. Then next part of it, Kirchhoff law. Based on Kirchhoff law, explain Kirchhoff law, state Kirchhoff law of current rule and voltage rule, and prove Wheatstone bridge, P by Q is equal to R by S, that derivation very frequently asked question. Then based on power, for example, two bulbs connected parallel to each other. This is 220 volt. Okay, this is 100 watt bulb, this is 60 watt bulb. Which bulb glows brighter? What the reason? We know resistance of the bulb P is equal to V squared by R. So R is equal to V squared by P. So your high power bulb will have low resistance. For example, 484. Low power bulb will have high resistance. That will get around 806.7 ohm. This is the way. So here, when we are connecting these bulbs in parallel, here we can say power is equal to V squared by R. Voltage is constant in parallel combination. P is inversely proportional to R. In that case, low power bulb will glow more brighter. Now, high power bulb with the low resistance. High power bulb with the low resistance glow more brighter. Now, same bulbs you are connecting in series. For example, this is 100 watt with the 484. Here 60 watt with 807. In series combination, current is same. P is equal to I squared R. So more resistance gives more brighter. So low power bulb with higher resistance 807 will give more brightness. So this question they can ask. Okay, based on this, how power, that power question, ratio of the power and all. Okay, then the violation of Ohm's law, that ohmic resistance and non-ohmic resistance. Okay, then another question, say a conductor of length L, area, this is stretched twice, and how does it affect resistance and resistivity? Or two graphs will be given, and T1, T2, which of the temperature is higher based on Ohm's law. These kind of 1 mark question also very important. This all in notebook, please go through it. Okay, but stress these points mainly. So this is about current electricity. Now next unit, third unit, magnetic effect of electric current. Then one more thing in current electricity, like this graph is given, which this voltage current, which region of the graph gives negative resistance. So this region gives negative resistance. That question also in the textbook, just go through it. The graphs are given there. Page number 101, the graphs are given, just you can have a look at it. Okay. Then next one, magnetic effect of electric current. In magnetic effect of electric current, first one we should know what is Byton-7 law. Then based on Byton-7 law, we have derived an equation. This one, magnetic field intensity at a distance due to a circular current carrying ring. This is important, and at the center of the ring, that's important, and due to a wire at a distance r, V is equal to mu 0 I by 2 pi r. This derivation also important. And in this derivation, there's a example question. Very frequently they ask that question. That's in the page number 1 minute. Let us flip the page. Yes. So here, in continuation with this one, Byton-7 law, page number 149. There is a solution, and just after that there is a graph like this. The graph is like this. Here B is proportional to R and B is inversely proportional to R. Here radius is less than R, radius equal to R, radius greater than R. Based on this question, repeatedly they asked 2-3 times in the previous board paper. So that question you have to examine, you have to go through page number 149 and 150. The question come. Okay. Then next, solenoid, we don't need derivation, we need only formula. Based on the formula, B is equal to mu 0 Ni. Numericals can be asked. So 2-3 numericals we have discussed in notebook. Just have a look at it. Or magnetic lines of force. They can ask to draw magnetic lines of force due to a current carrying solenoid. Okay. So based on that, questions can be asked. Then next one here, force. Lorentz magnetic force. That's very important. That means F is equal to BQV sine theta, or F is equal to Q into V cross V. Here F and V are perpendicular to each other. So based on this question can be asked, when a charged particle entering a magnetic field, how does it affect the change in kinetic energy? There is no change in kinetic energy can be done by a magnetic field on a charged particle. Usually magnetic field is used only to change the direction of charged particle, not to increase the speed. If you want to increase the speed, electric field should be applied to a charged particle, then only its speed will increase, kinetic energy will increase. So under any circumstances, if a question asked, when a charged particle placed in a magnetic field, moving any angle, any direction, it doesn't matter, you have to say change in kinetic energy 0, its speed will not increase, only this can be used to change the direction. And there are many special cases we know. When a charged particle entering parallel or anti-parallel, net force is 0, change in kinetic energy 0. When a charged particle entering perpendicular, the force acting is BQV sin BQV theta 90, that's equal to mv squared by r. From here r is equal to mv by bq. Based on this, question can be asked. And another thing, if this is a magnetic field, when a charged particle entering here, how does this path changing? Whether it is clockwise or anti-clockwise, based on that, question can be asked. Okay, this is all 1 mark question. For an alpha particle and a proton entering, what's the ratio there? Radii. That question can be asked. Another thing, they will give a magnetic field like this. Okay, and like this particle 1, this is particle 2. What is the nature of the charged particle entering this magnetic field? Okay, this is another type of question they can ask from here. Next one, force acting on a current carrying conductor placed in the magnetic field of another carrying conductor. Very, very important and repeated question. F by L is equal to mu 0 I1 I2 by 2 pi r. So here this producing a magnetic field here, and according to right hand Fleming rule, this is the direction of magnetic field. Then according to left hand Fleming rule, okay, here magnetic field is inward, then current is upward, it is an attraction. That means like charges repel, but like currents attract. Based on that policy, can show this direction of current. This is also an important question, and also related to this, they can ask, explain from this formula, obtain the SI unit of current, that is ampere. So this derivation, very frequently asked derivation, very, very important derivation. Then next most important one is moving coil galvanometer. So the derivation is very important. How can we increase the sensitivity of moving coil galvanometer? On number of turns we can increase, strength of the magnetic field increase, restoring torque per unit test should be decreased. These kind of questions are very important about moving coil galvanometer. And the role of radial magnetic field in a moving coil galvanometer also very important question. Okay, then conversion of galvanometer ammeter by connecting a shunt resistance parallel, conversion of galvanometer to voltmeter by connecting a high resistance in series with the galvanometer. These are the important areas we have to cover in. Which one? Magnetic effect of electric current. Then ampere circuit law also important. In using ampere circuit law, we are finding this one. B is equal to mu 0 N I. That is in the solenoid. Ampere circuit law is very, very important. Okay. Then, so the applications of ampere circuit law, that question can be asked. Solenoid, but there is no derivation for that. Then we have to go for electromagnetic, magnetism, magnetic material. So magnetic material, the main question they ask, they give a specimen. And if this is a uniform magnetic field, how it is modified? If it's a diamagnetic material, it goes like this. Ferromagnetic material means they all go inward. So based on this, question can be asked. Or they will give you specimen, they will tell you identify the material placed here. Or same question can be asked, susceptibility they may give minus value and some plus value. If it is negative value, that is diamagnetic material, plus value, that is ferromagnetic material, greater than 1, slightly greater than 1, paramagnetic material. So you should be able to identify this paramagnetic, diamagnetic and ferromagnetic with the proper examples. Okay, so that is very commonly asked question from here. Or electrostatic, when we study, same thing, torque acting on electric dipole, torque acting on magnetic dipole. work done in turning electric dipole, work done in turning magnetic dipole. So these all analogous, connected you have to study. Electrostatic when studying, magnetism also you should study. Then intensity along axial line of electric dipole, intensity along axial line of magnetic dipole. So in this case, you should read the question completely, whether it is electric dipole or magnetic dipole. There are chances of making mistakes. Okay, so both similar pattern, but one is electric dipole, other is magnetic dipole. So this is the main thing that we have to cover there, right? Then next one in magnetism. Then after that, electromagnetic induction. In electromagnetic induction, Faraday's law of electromagnetic induction is very, very important. Based on that, question can be asked. For example, if there is a ring and current flowing here, what will be the polarity here? Okay, if the current increasing here, okay, then here magnetic field increasing, this will act like north pole, current is anti-clockwise. This kind of question can be asked from here. After this, then from this conceptual question can be asked. And when a solenoid here, when a magnet is dropping, its field decreasing. Why it is decreasing? That's because of induced current. Lenz's law, mainly Lenz's law, we can say. Because of Lenz's law, this movement is opposed. That kind of questions can be asked here. Next one, they can ask here self-induction derivation, very frequently asked question. L is equal to mu 0 N squared A. This derivation is very, very important. Then mutual induction also important one. M is equal to mu 0 N1 N2 A divided by L. And for two wires, this also once they ask. This is now two rings, mutual inductance between two rings also very important derivation. So any question can be asked from here. Okay. Then next one, this one, generator. Generator is very, very important category of 5-mark question. Explain with the diagram how a generator is working, and until that formula obtained, E is equal to E0 sin omega t, I is equal to I0 sin omega t. This is important 5-mark category question or case-based study question. Okay, and the graph also you have to mark. This is voltage variation, this is current variation, this is instantaneous value of EMF, and maximum value of EMF is NBA omega. This is very important question. Then another thing, motional EMF. E is equal to BLD. Here derivation and numericals are also equal. Then E is equal to half BL squared omega. Very, very important numerical. This half BL squared omega. When a metal rod is rotating in magnetic field, metal rod of length rotating in magnetic field, this is induced EMF between axis and the ring. Same question in generator will come, a coil rotating in magnetic field, NBA omega. Here students make mistake. When you're reading rotation, you go to usually which one? Either this one or confused to generator. You must make sure that generator means they will not specify the term generator. Usually they a rectangular coil or circular coil rotating in magnetic field. In that case, you have to use the formula NBA omega. But a metal rod, if it's moving, metal rod, if it's moving, then you have to use this formula. This is motional EMF. Okay, so this also chances of making mistake must be very clear that there is chance of asking question. Almost 99% you get a question from generator. Then next one comes to transformer. In transformer, also very, very important 5-mark category, the transformer ratio until ES by EP is equal to NS by NP is equal to IP by AS based on this. And numerical also can be asked from transformer. Important 5-mark question this time. Definite question that one. Okay? We can say almost 100% chances are there, this transformer. Right? Then another question from AC they can ask using phasor diagrams. Okay? Using phasor diagrams. We have to prove in resistance there is no phase lag between voltage and current. In pure inductance, phase lag is minus pi by 2, and pure capacitance plus pi by 2. This kind of question can be asked in 2-mark category. And another question, LCR circuit. Okay, in LCR circuit, obtain the expression for inductance using this phasor diagram. That is root of R squared plus XL minus X whole squared. Another question, resonance frequency 1 by 2 pi root of LC, and the graph. This is XL frequency graph, and here XC frequency graph, Then this is impedance frequency graph, and here next one current frequency graph. Current frequency graph, it goes like this. So these all graphs are very important. You should be very clear about it. This is inductive reactance frequency, capacitive reactance frequency, impedance and frequency. This is current and frequency. So this LCR circuit, that derivation is very important. Similarly, power. Power is equal to ERMS, IRMS. All 5 questions are important. Then using RMS value, they may give an RMS value. They will ask you to find out peak value of it. These are all example questions we have referred in the notebook. Okay, so just go through the exercise in the notebook. That's very important. Then lastly, we are going with AC current and electromagnetic waves, already we discussed in the previous session. So these are the more important areas that you have to cover, and the link of my notes completely I will upload, then that link will be given. So go through these important areas, and derivations I told you, that derivations first you finish. First what you have to do, finish entire derivations, complete derivations in the notebook I have given, which is not important. Then we have to do with all numericals given in notebook. Then next stage we have to go with all important conceptual questions. Okay. After this, go to textbook all that boxed one questions. Right. Then previous year paper. This is a category, and always choose the easiest chapter. I told you. First you have to finish semiconductor, then atomic nuclei and atoms and nuclei. Then go for dual nature. These 3 chapters, if you are covering itself, you will get passing mark. Then scoring, telescope, microscope, if you are studying itself, definitely you will get 1 question, 5 mark question from there. So optical instruments. Then go for lens makers formula, that chapters. After that only go to drift velocity, current electricity, that areas. Okay. So anyway, this way if you plan it and learn within short time, okay, definitely you can get successful in your exam with very high percentage. Best wishes. Come out with flying colors in the coming examination. Thank you for listening to me. Thank you.